Hey everyone! Today I want to show you how a wave can be turned into a particle. I must admit that this video is the most elaborate one I've ever made, and therefore it's also quite long. And the most interesting part is actually at the end of this video. So if you have very little time, my suggestion would be to at least check out that part where we catch waves and turn them into particles. For the rest of the viewers, I will start off by discussing the essential background that you need to truly understand how this works. I'm first going to discuss the inertia of confined energy. I'll continue with explaining nonlinear elasticity in media and what it means for the vacuum to be a medium. And after the break, I will quickly discuss the circumstances where the vacuum starts to behave nonlinearly. Then we are going to create a simplified 2D model, do some simulations and create the circumstances under which waves can confine themselves and effectively turn into particles. So let's get right into it. I want to start by discussing a paper that a viewer named Wammes Waggel pointed out to me named Light is Heavy from the year 2000. It's a paper by Martin van der Mark and Gerard at Hooft, published in a somewhat obscure magazine, but it immediately attracted my attention. Not only do I know Martin from my time at Philips Research, his co-author was Gerard at Hooft, the 1999 Physics Nobel Prize winner. So naturally I got curious about the content of this paper. Now it's a great paper that explains how light can have inertia and weight, even though it does not have rest mass, like a particle does, and that is because it represents energy and momentum. And since the perspective of the paper aligns well with an introduction that I had in mind for this video, I decided to use its storyline to explain the inertial mass of light. So a huge thanks to Martin, Gerard and of course Manuel. Say that we have this isolated block of material with a mass m freely floating in the vacuum of space. To accelerate this object and let it gain momentum, we have to apply a force. And this is the essence of the inertial aspect of an object having mass. The persistence to stay in the same state of motion, or in other words, its resistance against being accelerated under the influence of external forces. And of course, more massive objects have a higher resistance to acceleration. If this object were to be placed in a gravitational field of another object, like for example Earth, which has quite a bit more inertia, the two objects will start accelerating towards each other. In fact, the gravitational pull on both objects is equal and in opposite directions, but since the Earth is so much heavier than the object, its acceleration will be proportionally smaller and can be neglected. Now note that even though these objects are both accelerating, no external forces are currently applied on either object. And what we can do in order to stop these two objects from approaching each other is to exert a force on either or both objects opposite to the direction of attraction. In fact, it doesn't really matter whether we do this by using a rocket or separate the two by using a party table. As long as we compensate for the attraction by opposing forces, we can prevent them from getting closer to each other. Now, from the perspective of an object with mass, the situation of being stationary in a gravitational field or being accelerated in free space is completely equivalent, and this inspired Albert Einstein to formulate the equivalence principle. And therefore, inertial mass and gravitational mass are basically the same thing. Okay, so the situation with a single massive object is fairly easy to imagine. Now let's take the next step. We're again in the vacuum of free space, but now we have this container which is made of a very light material. In fact, the mass of this container is so small that it can be neglected compared to anything we put inside it. And what we now do is insert a gas consisting of individual molecules that are freely moving through space. Each molecule is a tiny amount of matter, so all these molecules together represent a specific amount of mass. To us observers, which are stationary to this container, the total net momentum of the gas is currently zero, even though the individual molecules are basically moving at high velocity, and they bump into the walls of the container and exert a pressure on the walls, which is on average equal in all directions. Now, even though individual molecules appear to be moving freely through space, Their movements are of course limited by the confinement, and therefore accelerating this container requires a force. The easiest way to see why this must be the case is just to consider two individual molecules that were on their way to bumping into the opposite walls. During the acceleration of the container, the molecules on one side will hit the container wall on average with a higher speed and thus transfer more momentum. At the other side, a similar molecule will transfer less momentum than had the box been unaccelerated. And because there's a lot of them, the molecules as a whole will resist the acceleration because of a pressure difference that arises between the two walls. Again, a similar reasoning holds for gas molecules in a gravitational field, and essentially this is the reason why there is a pressure gradient in our atmosphere, because eventually it all comes down to individual atoms or molecules in the gas either being accelerated or decelerated by Earth's gravitational field. The final step is that we now take this same container that itself has little or no inertial mass and make its walls 100% reflective on the inside. And this container is again placed in the darkness of free space. Instead of filling it with a gas, we will insert an amount of electromagnetic radiation in the box, light basically. So my question to you is whether this box has gained inertial mass because of the light inside. I guess the first reaction of many people is probably that this is not the case, and that is because, contrary to molecules of matter, light has no rest mass. But it turns out that filling the container with light does add additional inertial mass. The reason for this is that light represents an amount of energy and momentum, and it actually also exerts a pressure on the walls. May sound weird that light exerts a pressure, but it's actually the physics behind what is also referred to as solar wind. It's the force exerted by light that can in principle be used to accelerate spaceships away from a bright light source like the sun by using giant reflective sails. Let me just quickly try to summarize where this pressure is coming from. In fact, it doesn't really matter whether you consider light to be a number of quantized interactions with a wall, each representing a specific amount of energy and momentum, or you consider light to be a classical wave with intensity. Let's for a change explain it using the quantum description of light now. The momentum transferred by a quantum depends on its frequency, and during acceleration, a Doppler shift is introduced between the walls, shifting the frequency to a higher value on one side and a lower value on the other side. And with many quanta, acceleration leads to a net difference in the transfer of momentum, which is equivalent to a pressure difference. The effect is very similar to the case of molecules hitting the walls, and so light too will resist acceleration and as a consequence have inertial mass. So concluding, if you put light in a box, it has inertial and gravitational mass, and therefore light is heavy, although maybe not that heavy. If we were to release 100 joules of radiation into a confined space, its inertial mass is equivalent to 100 divided by c squared is 1.1 times 10 to the minus 15 kilograms, so about 1 picogram, which is not very much. But of course, it's not zero. And if you look at the equivalent of a gas consisting of molecules, say nitrogen molecules, a container having an identical inertial mass of 100 joules of light would still have to contain 24 billion atoms of nitrogen. But maybe the weirdest part of it all is that by containing light in a weightless box, you cannot accelerate this box to the speed of light anymore, even though the light inside can only travel at the speed of light. And the underlying reason is of course that this system has inertial mass. Now I don't want to dig deeper in that direction. Let's instead consider a nice thought experiment from the paper about what were to happen if you fill this container with electron and positron pairs. These two types of particles can annihilate when they meet up, which leads to the creation of gamma radiation, so electromagnetic radiation with a very short wavelength. Of course, this is a somewhat theoretical thought experiment because in practice it would be very hard to do, but what you would observe is that the inertial mass of this system remains identical during the conversion process, and that is because inertia is in essence not about mass, it's about energy. And so it doesn't matter whether that energy is in the form of a particle or as radiation. Given that particles with mass and electromagnetic radiation have identical inertia and additionally can transform from one state to the other, you might maybe wonder whether all matter is just radiation that got spatially confined somehow. In other words, particles might just be some kind of self-confined light. Of course, self-confinement of wave energy is not really a trivial concept, and around an elementary particle, like for example an electron, there is no such thing as a little box to contain the rather high internal energy. The only thing literally there is empty space or the vacuum. So that is what we're going to look into. See if we can assign properties to the vacuum that can lead to self-confinement of energy. Now, to make it look like we're doing serious science here, I will state that this is our little theory. A particle is spatially confined or trapped light. And as a basis for the theory, I will make a few assumptions or suppositions that can offer an explanation of how this is possible. And don't worry, I will discuss these assumptions in a lot of detail in just a second. Then we'll create a model and do some experiments, which in this case are simulations, and hopefully the results we get are in support of our theory. Now, it's essential that you understand the meaning of the two assumptions. What does it mean for the vacuum to be an elastic, non-linear medium, and how can light and matter be perturbations in the vacuum? So what I'll do is explain the concepts highlighted here one by one in the next couple of minutes. Let's begin with the word elastic and use the example of a ball bouncing on a surface. In the case that this process is completely elastic, the total energy of the ball and the surface is the same before and after the collision. During the collision, the ball deforms and decelerates at the same time, and during that time, kinetic energy is stored in elastic deformation. Then the ball tries to return to its original shape and in the process gives the energy back as kinetic energy to the ball. And if this process is fully elastic, it means that none of the original energy gets trapped or sidetracked in some way during the deformation, and all the energy stored as elastic deformation is returned to the ball. In the case of inelastic deformation, however, some of the energy might have converted into heat during deformation, and the result is that eventually some of the energy gets lost in the process as heat, but in systems that are truly elastic, that doesn't happen, and energy storage by deformation is completely reversible. Okay, let's now focus on non-linearity in relation with elasticity. And for this, we'll take an example of extending an elastic rubber band. If we extend an elastic band slowly over a short distance, the deformation will follow a linear relationship with the force or pressure applied to the material. For convenience, I will refer to applying a force or a pressure as applying stress. So that is summarized in this formula. Deformation d is the stress epsilon divided by the stiffness or elastic modulus E of the material. And in a material that is linearly elastic, the modulus E has a constant value regardless of stress. This is illustrated in these graphs. We observe a constant value for the modulus as a function of stress, and this results in a linear relation between deformation and stress. If we keep extending the rubber band, we get into a region where it becomes increasingly difficult to extend it any further. So what happens is that the modulus is not a constant, but it is a function of stress. This is again illustrated in two graphs. In the left graph, we observe that the modulus is not a constant but increases with the absolute value of the stress. And in the right graph, we observe what this means for the deformation as a function of stress. At low stress levels, the relation is predominantly linear. However, as the stress increases, the magnitude of the deformation is lagging behind compared to purely elastic behavior. To describe this type of relationship, we need to specify how the modulus is a function of stress. And to do that, we could, for example, use an equation like this one. Here, the elastic modulus is equal to the modulus at zero stress multiplied by a factor to correct for the effect that stress has on the modulus. In this particular formula, we can use two separate parameters to describe the nature of the deviation from linear behavior. First, there is the non-linearity coefficient alpha that describes the magnitude of the non-linearity, and additionally, there is the exponent n that describes the curvature found in the non-linear behavior. Now, using this formula, we can describe many different types of nonlinearity by varying the values of alpha and n. And to illustrate how the values of alpha and n can influence nonlinearity, I'm showing you just a few random examples of how modulus and deformation are related for different values of alpha and n. Now, let me emphasize that nonlinearity and elasticity are fundamentally two different things. Elasticity is about conservation of a specific type of energy in a system, and nonlinearity is in this case about the relationship between stress and stiffness, and in essence about how the energy is stored. So a system can behave non-linearly but still be completely elastic. The last thing I want to explain is what it means for the vacuum to be a medium and light and matter to be perturbations of the vacuum. And conceptually, I think this is the most difficult idea to explain. In the absence of any radiation or particles, the vacuum is empty space, devoid of any energy, at least not any that we can observe. But in fact, all major theories concerned with space assume in some way that the vacuum must contain a base level of energy. And this base level is called the vacuum energy. So if we, for example, take the vacuum energy on cosmological scales, we see that it's estimated to be 10 to the minus 9 joules per cubic meter. And this value follows from the observation that our part of the universe is expanding against gravity. But if you look at theories that are concerned with elementary interactions, you see that a somewhat less conservative value for the vacuum energy must be assumed. And this incredibly high value is required to account for virtual photons and particles popping in and out of existence from the vacuum, which are needed to explain quantum interactions. So there's quite a big discrepancy between theories as to the energy content of the vacuum. Now, regardless of the exact value stated here, I guess the question is, can the vacuum energy be different at different scales? And the answer is, in principle, yes. The concept of energy itself is actually pretty complex, if only because we distinguish so many different types of energy, like potential energy that can by itself come in many forms or fields, or kinetic energy, chemical energy, or nuclear, radiant, thermal energy. But what all of these types of energy have in common is that they can do work. And this is actually the definition of the energy of a system, the ability to do work. I agree, this sounds as a definition from the steam engine era, but it's still very much the essence of energy as it is perceived by us. There's a little catch though. For a system to perform work, we always need some kind of difference or gradient in, let's call it, the energy density. So take for example thermal energy. We can only have a steam engine do work for us if there is a gradient in temperature, so a gradient in the energy content of space. And it cannot perform work if you place it in an environment of uniform thermal energy, no matter how high the energy content is. Or if you want a compressed spring do work in an environment that contains an identical and uniform level of stress. And this aspect can be a bit confusing at times. On the one hand, we talk about energy as a property that has density in space, and on the other hand, we describe energy as the ability to do work, for which we need fluctuations in that same property. And this shows that the meaning of the word energy varies with the context in which it is used. Let's return to the huge difference in vacuum energy as a function of scale. If we assume that there are large fluctuations in the energy density of space on very small scales, these can do a lot of work on elementary particles like electrons or atomic nuclei, for example, facilitate nuclear decay, and together all these high frequency fluctuations will effectively amount to a huge energy density of space. However, if we consider the ability to do work on a somewhat larger scale, for example between these two areas, it would diminish rapidly with dimension, and that is because the energy density differences between the two areas have become much less significant. And if we zoom out further, for example to the human scale, the energy density fluctuations have become insignificant, and we observe a uniform medium that cannot do any work for us. Yet on cosmic scales, the energy density fluctuations might again be significant enough to perform the work needed to counteract gravity and expand space. So, concluding, it's not that weird to consider the vacuum of space to be an elastic medium that contains very high frequency energy or stress fluctuations that are uniformly distributed in space, and that radiation and matter are the energy fluctuations superimposed on this base level which are observable to us. And maybe by assigning non-linear properties to the elasticity of space, we can demonstrate how particles can form when wave energy gets trapped locally. Now, at this point, it's probably a good idea to pause the video for a moment, turn your eyes away from the screen, get up, move around a bit, maybe get a drink, and prepare yourself for what is about to come next. So let me quickly get a drink myself because all this talk made me very thirsty. Oeh, zo, droge bek jongen. Okay, let's continue. Now, there's one important point that I didn't address before the break, and that is why the vacuum would have non-linear properties in the first place. Because all experiments with, for example, visible light show that the vacuum is a linear medium. For example, we cannot with current laser technology make two light beams interact in the vacuum. Here is a schematic 2D simulation of two waves meeting up in a linear medium. One wave is continuous, the other one is pulsed, and what you observe is that although the waves locally interfere, they still go their own way completely unchanged. And this is what we also see with light. We can observe interference, but we cannot observe physical interaction, like for example the exchange of momentum between waves. We can actually make light behave in a nonlinear way, but for that we need to create very high fields inside special crystals. However, such phenomena never seem to happen in the vacuum. Theoretically though, there is a field value above which the vacuum must also start to behave nonlinearly, and this value is called the Schwinger limit. This limit is named after Julian Schwinger, a theoretical physicist, and its value is approximately 1.3 times 10 to the 18 volts per meter, which is huge. Even with the most powerful lasers, we are currently still more than an order of magnitude away from reaching it. Note that the Schwinger limit is an approximation, and that is because the definition of the term nonlinear behavior is kind of vague. It really depends on how large the effect on behavior is that you are looking for in order to call it nonlinear. But from the units, it's clear that the Schwinger limit is an electric field value, so a potential difference per unit of distance. The general reasoning behind space behaving nonlinearly above a certain field is based on the experimental observation that energy can transition between radiation and particles with mass. Earlier in the video, we discussed the annihilation of electron and positron particle pairs, resulting in the creation of gamma radiation, but this process can also proceed in the opposite direction if we locally have sufficient energy available in the radiative field. The amount of energy we need to create these two particles can be calculated, and it's 2 times the electron mass times the speed of light squared. And in order to produce at least this amount of energy from radiation, a specific minimum frequency is required, which is very high. It's about 500,000 times higher than the frequency of visible light. From the perspective of quantum mechanics, the conversion is just an energy balance in which the frequency of the radiation and the total mass created have to match. But as we just saw, the Schwinger limit is a field value, and the way it is derived is from the ability of an electric field to do work within the dimensions of a Compton wavelength. And this energy equals the charge of the electron times the field value times the Compton wavelength. I will not discuss the meaning of Compton wavelength here, other than to refer you to a very good video about the subject. Now if you look at the minimum or critical field needed for this particular conversion and rewrite the energy balance as it is stated here, we find a value of 2.7 times 10 to the 18 volts per meter for the minimum field. And for those of you that paid attention, this value is actually 2 times the value mentioned earlier for the Schwinger limit, but that is because here the non-linear behavior resulted in the creation of 2 particles and not a single one. If you have seen previous videos of mine, you know that I love to do 2D wave simulations because they can be extremely helpful in visualizing and understanding wave phenomena. Of course, you should always keep in mind that these simulations are a strongly simplified representation. So next we're going to do some simulations that include non-linear behavior. As a basis for the simulations, I use a Python script supplied to me by @diffraction Limited. I'm very grateful to him for this, including the help in realizing the simulations. And if you want to try this type of simulation yourself, please refer to the video description for more info and download links. I don't want to go deep into how the software works, but instead globally explain the model. In the simulation, every pixel represents a cell or an element, and each element contains certain data like values of the potential and kinetic energy content and data about the local elastic properties of the medium. A cell is connected to its next neighbors by elasticity, which is represented by a set of springs in this image. And we can also specify damping or energy loss between elements in the model, which is in this case schematically represented as these little dampers or shock absorbers. However, since we want the medium to be fully elastic, we don't use damping in the simulation area other than at the very edges, and here damping is just intended to avoid waves reflecting off the walls back into the simulation. So this is basically a representation of the model, and the numerical equivalent of this model allows us to see how waves propagate through the medium as a combination of potential and kinetic energy. Now, I modified the original Python script a bit, and the way that my version of the simulation works is that you import an RGB image that describes the key aspects of the simulation space. The green values in the image contain the potential energy distribution with which to start. The elastic modulus of the medium is encoded in the red channel, and for the current simulations, this property has a uniform value in space for the starting condition. And implemented in the blue channel is damping, only present in the pixels at the borders to avoid reflections. So these 3 aspects are combined in a single image and define the starting condition for the simulation. What I need to explain here is that the potential energy distribution is basically elastic stress encoded in the medium. But if you look at the values themselves in this 3D plot, you must conclude that these are actually not field values, because a field value is a potential difference per distance, as we've just noted with the Schwinger limit. So in order to go from potential to field value, we need to calculate the change or derivative of the potential energy distribution. And here you see what that looks like. The variations in field strength have 2 times the spatial frequency of the original wave pattern, because there are 2 slopes in each wave cycle. And since space should behave non-linearly with respect to the field value, we insert these field values into the non-linearity equation to calculate the elasticity modulus as a function of position. And then we use that distribution for the medium. Next, we let the wave energy propagate 1 time step in this medium, which gives us the new potential and kinetic energy distribution, and we feed these data back into step 1. And then of course we repeat this procedure for a large number of simulation cycles. Okay, let's quickly look at what such a simulation looks like for an elastic medium. This image contains our data for the initial wave condition. The contents of the green channel in this image is converted to positive and negative amplitude for the deformation, which contains the potential energy, and negative and positive potential values are indicated in a blue and red color. And now we let this potential energy distribution relax and distribute its internal energy into the medium. Observe how the wave energy propagates both outward as well as inward. the part of the wave energy that moves inward, passes the center of the pattern and then proceeds to move away again. Okay, so far so good. Now the next thing is to simulate a non-linear medium instead of a linear one, and what we can do now is tweak the non-linearity of the medium using the parameters alpha and n. The goal is of course to see whether we can make waves that somehow contain themselves. And this is where things got really frustrating because I didn't know where to look exactly. I initially just filled in more or less random values for alpha and n, but basically this did not work at all. I did, however, encounter several problems, and one is concerned with the total energy in the simulation field, which is illustrated in this example. At some point in the simulation, the amplitude suddenly increases for no apparent reason, and this is of course a result of the non-linearity of the calculations, but also because we take finite time steps in the simulation. So let me explain. If you consider an elastic spring that you extend by a length of delta x, the extra energy stored in the spring, delta E, amounts to 0.5 times the spring constant times the deformation squared. But if your simulation works in discrete time steps, you calculate the value of delta x based on the initial value of k, then you correct the value of k using the nonlinear relationship for the new stress level, which is related to delta x, and this correction can also increase the total energy contained in the spring. Of course, there's no physical origin for this extra energy, so it's clearly an artifact of the calculation itself, and it's definitely undesired. Now what you can do is to normalize the total wave energy in the field between each step so that it remains identical during the simulation, and this definitely helps, but I found that this can also lead to other types of artifacts and even instabilities. Now another very obvious artifact is the weird diagonal symmetry in the pattern, which is also a result of the calculation method. The calculation of the elastic interaction of a cell with its 8 next neighbors is based on a Laplace transformation matrix, but due to the numerical limitations imposed by using this matrix, the method can lead to a weird diagonal symmetry in the results. And I found that it is especially unavoidable in the case of very high field values and high spatial frequencies. So unfortunately you will observe this diagonal symmetry in every simulation that follows, and I cannot avoid it. But this symmetry aspect is something we should at least try to completely ignore, because without the numerical limitations of the calculation method, patterns should always be circularly symmetric. Now, after a lot of trials, I could not get the simulations to produce anything resembling a self-confined state. And in an act of desperation, or maybe call it genius, I decided to make the exponent n in the nonlinearity equation negative. And this yielded a very curious simulation result, which I want to show you. So in this particular simulation, the total energy contained blows up and increases quite a bit during the simulation. But watch how the negative and positive amplitudes got confined to separate areas in space. So in this case, red is a positive potential, blue is a negative potential. And what you observe is that the amplitudes get stuck in specific areas of the simulation space. So when I first saw this, I had no clue what was happening, and it was only after I plotted the nonlinearity function that this made any sense. Here you see what a negative exponent means for the elastic modulus as a function of stress. Effectively, the stress value goes into the denominator, meaning that around zero stress the elastic modulus goes to infinity. And maybe the easiest way to explain what happens in this particular case is to use a spring as an illustration. If the deformation of your spring is on either side of zero stress, it can never get to the other side, because the elastic modulus is infinite at zero deformation. And so going from positive to negative would require an infinite amount of energy. And that is why the amplitude becomes confined. Of course, this wasn't what I was looking for at all, but it actually gave me an idea where to look next. Because what I wanted to achieve was something very similar. So energy trapping in space, but not at zero stress level, but at a high stress level. And a way that you can achieve this is by using a high value in the exponent value n and use a relatively low value for the elastic coefficient alpha. The result is shown in these plots. So starting from zero stress, we see that the elastic modulus is more or less constant at low stress levels and at some point increases dramatically because of the high value of the exponent. If we look at deformation, we first find ourselves in a region where behavior is mostly linear, but at some point we see that non-linearity takes over and results in a maximum deformation. And when we increase the stress further, we observe that it becomes energetically more favorable for the medium to contract. It's difficult to envision a spring equivalent for the state that the medium and the energy go into. Basically what happens is that if the stress level increases, the medium will shrink. And because there are no true physical boundaries here, the result is that the energy will strive to confine itself to the smallest possible dimension. But on the other side of this process is the elastic modulus, which is strongly increasing with stress, and this sets the lower limit to the shrinking. Now the result is that the system has entered a state from which it cannot return to the linear region without supplying it at least some additional energy, and so basically this stress got stuck and with it the energy that went into the deformation. Now, if you did not understand what I just said, I don't blame you. Luckily, I have some simulations to illustrate a few aspects visually. And what I will do is start off with two relatively low spatial frequencies as the initial conditions, which are shown here. Now, if we release these into a nonlinear medium with the properties for alpha and n as discussed, we observed nothing resembling energy confinement. In both cases, they behave sort of like a wave would in a linear medium, and that is because we are still largely in the field range where linear behavior is dominant. So here's a somewhat higher frequency pattern, and in this case I will show two graphs. To the left the wave pattern as it collapses, and to the right a representation of the elastic modulus of the medium. Here we go. I'm not sure you noticed, but in the center of the pattern you could actually observe the nonlinear behavior of the medium kick in. However, it was not stable enough and very quickly dissolved again. Okay, now let's push a wave over the edge by using an even higher frequency starting condition. What you can now observe is that in the center of the simulation, the medium goes into the region of nonlinear behavior. So what happens here is that we exceed what you might refer to as the Schwinger limit for this medium. And we can observe how a part of the wave energy got trapped in the medium and a small particle is formed. Here things are zoomed in a bit. To the left the field, and to the right I've added the elastic modulus of the medium. And what you observe is that the trapped energy initially has the diagonal symmetry, and of course this is related to the limitations of the Laplace transformation matrix in combination with a very high field. But at some point the simulation becomes unstable due to other numerical errors, and the particle continues to evaporate while it's emitting radiation. To the right you observe how the medium adapts in an attempt to keep the energy in the particle confined. Unfortunately, in vain. What happens is that the numerical errors in the simulation allow the field to locally fall below the Schwinger limit, and the result is that the energy becomes mobile again and can escape into the medium as wave energy. So this particle isn't really stable, but I think it shows that you can at least temporarily store energy in non-linear elastic stress. The next question is, of course, can we avoid these instabilities? And it turns out you can with a dirty trick. In the last few simulations that I showed, the energy blow-up we discussed earlier was actually artificially suppressed by limiting the total energy present in the simulation. But if we remove this energy suppression mechanism, we can make particles that, although they are gaining more and more internal energy, are much more stable. The reason is that by allowing the stress or the field in the simulation to grow slowly, we can overrule the numerical instabilities that can lead to the demise of the particle. And this is such a stable particle. Now, due to the growing amplitude, it's difficult to see the internal structure. But the most amazing part to me is that the contents appear to be more or less static in space. It's not some oscillating standing wave with a frequency, as I had personally expected, but static stress. Basically, the wave energy is converted into pure elastic potential energy which cannot be converted back and thus got stuck in the medium. At first I had trouble believing that this could in fact be real, but gradually it started to make a lot more sense, as I will discuss in a minute. But first I want to point out this crazy effect in the elasticity modulus of the medium. Here it's using its non-linearity to very effectively resist a growing field amplitude inside a particle. In this graphical representation of the elastic modulus, we observe that the medium is constantly adapting its properties. The grayscales are indicative of variations in the local elastic modulus of the medium within a very specific range. Outside the pattern, the variations are too low to observe. Inside the particle, they're actually too high. But in this boundary, we can observe how the medium manages to contain the growing energy pressure that is slowly building up inside the particle. And what this shows, in my opinion, is that nonlinear elastic confinement can in principle be very stable and resilient in the absence of any numerical instabilities. So if we turn back to our little theory, I feel that the simulations are in support of the assumption that you can, in theory, locally confine wave energy by assigning nonlinear properties to a medium. Of course, this model is not a simulation of light in 3D space, nor is it in any way a simulation of how real particles are created. It's only a very crude 2D model that contains a lot of artifacts. But I think that the concept behind it all, of space being a nonlinear medium, is extremely fascinating. So where to go from here with our little theory? Well, the current nonlinear equation only has field stress as a parameter, and this leads to every simulation striving for maximum stress levels. In the simulations, this leads to field value maximization between individual pixels, so we can never really zoom in. Therefore, the next step would be to find a better nonlinear equation, one that also considers energy conservation and the energy density in space. Let me, as a final note, give you a few additional insights why energy stored as static stress makes more sense than you might initially expect. What I found is that the stress involved in the energy of a particle is never truly localized. If you look at the 3D representation, you see that most of the energy is stored as high spatial frequency stress, but outside this core, it also extends into space. Here you see two cross-sections, which I took along the diagonal and horizontal axis, that show the stored field stress. So even though most of the energy in the particle is locally confined in the core, the presence of the full particle extends in space. And I guess a moving or accelerating particle will communicate its presence to the rest of the universe through the part that extends into space. I also found that you can freeze potential energy values in such a way that the particles have a specific sign in the field stress outside the core. In the top images, this sign is indicated as a color, again red and blue. In the bottom you see a 3D plot, and as we've just seen, this sign extends into space. But maybe the most illustrative thing is to look at cross-sections of the particles, where this sign is most obvious. Now, stress values of opposite sign can of course cancel each other out. So it will in fact be energetically favorable for particles of opposite stress sign to be in each other's vicinity, which effectively means that particles with this opposite stress imbalance will experience something resembling an attractive force. And this net imbalance of frozen amplitude in a particle is very similar to something we generally associate with charge. So electromagnetic fields are the result of accelerating charge, but this here indicates that charge itself could very well be electromagnetic field asymmetry that got frozen in space. The nonlinearity as it was proposed in the model is completely symmetric with respect to the sign of the stress. If we schematically represent the solidified energy in a particle as this simplified static stress pattern, it's easy to see why every particle must have an equivalent antiparticle that contains inverse stress, has an inverse sign, and at the same time holds an identical amount of energy. Now the last thing I want to mention is the following. Say we have this particle and we assume that its energy is indeed stored as field amplitude that was frozen in space. That particle by itself does of course not have to be static, because there are no fundamental restrictions why this energy could not be moved around. But due to the energy confined, it would have inertia. Now say we want to measure the wave inside the particle at this line. For this to work, the particle has to be moving. If it moves slowly, we will measure it to have a long wavelength. If we increase its momentum by changing its velocity, we will measure a higher frequency and thus a shorter wavelength. And so this particle carries with it a fictitious wave associated with its movement. And that might actually be all there is to it, Louis.